So welcome once again to Focus Private Tuition. I'm your host, Say Shungu. So in this particular video, we're going to be talking about how you can measure the rate of a chemical reaction. We're also going to look at factors that affect the rate of a chemical reaction at the end of this video. So let's go straight into it. So when you're measuring the rate of a chemical reaction, you need to know the amount of reactants that are used over a specific period of time, or you can use the amount of products that are formed over a specific period of time. So you need a way to measure the amount of product formed. You also need a way to measure the amount of reactants that is used. So you can use mass or you can use volume if one of your products is a gas. And you also need to measure your time. So let's look at an example here. You have magnesium plus hydrochloric acid to give you a salt and hydrogen gas. So let's suppose that you're told that this reaction produces 1,200 cubic centimeters of hydrogen gas over a period of 4 minutes. Then with this information, you can calculate the rate of reaction and say your 1,200 cubic centimeters divided by your total time in seconds, 4 times 60, and you get 240. If you divide, you get 5 cubic centimeters per second. So this is the average speed because the assumption here is that per every second you were producing 5 cubic centimeters. So these are even volumes of your product which are formed per second. But this is not true in most of the cases, since at the beginning most reactions happen quickly, since you have a large concentration of your reactants, and they slow down and eventually they stop. So this is the average. But you can also calculate, you can be more specific and calculate the amount of product produced per specific time period. So we'll look at this later on. Okay, so suppose you could monitor each second the amount of hydrogen that is produced. You can plot a graph, and like I said before, so on your y-axis there you have the volume of hydrogen produced, and on your x-axis you have time. So like I said before, at the beginning you're going to have a steep curve because you have a large concentration of the reactant, and hence your reaction is going to be fast at the beginning, and it's going to slow down a little. So our curve gets becomes gentle, and eventually it flattens out as the reaction stops. So what you can do with this graph is you can calculate the average rate like we did before at a specific time period. After a specific time period, for example, what is the mean rate of reaction in the first 3 minutes? So what you can simply do is identify your 3 minutes on the graph, and then what you do is you draw a dotted line on that graph towards the graph, and see where it intercepts your graph. From there you draw another line towards your y-axis and you measure the volume there. So as before, after 3 minutes here we have 1,200 cubic centimeters, and we divide the two to get an average rate of 6.67 cubic centimeters per second. But you can also calculate the actual rate at a particular time, like I said before. So for example, what is the rate of reaction at exactly 2 minutes? So identify 2 minutes, draw a dotted line which intercepts your curve, and instead here what you do is you draw a tangent at that point, a tangent which touches the curve. And now what you do is you must be able to calculate the gradient of that tangent, which is given by change in y over change in x. So you need to measure. So here for our change in y, that would be the volume of hydrogen produced, and our change in x is going to be change in time. So what you have to do is you have to draw your tangent long enough so that it intercepts your y-axis, and after doing that you draw a dotted line towards the y-axis as shown there, and you draw another dotted line towards your x-axis. And so now you're ready. You can measure the change in y which would be from the point your tangent intercepts the y-axis to the top of that tangent. In my example here, it's 600 cubic centimeters. So that would be the difference, 600 cubic centimeters of those 2 points. And for the change in time there, that would be equal to 2 minutes 50 seconds. So once you have those two values, you can substitute and you get your rate at that particular point of 3.53 cubic centimeters per second. Okay, so this is how you would calculate the rate at a specific point in time. You must practice this on a piece of graph paper so that you get used to drawing the tangent and getting values from your tangent line. Okay, this can also be done if you measured the amount of reactant that remains or that is used. So here we have the amount of magnesium that remains. So as the reaction progresses, we expect our magnesium to decrease, and here is a plot of the magnesium that remains per given time. So it's going to decrease. Initially it's going to be steeper. Again, it gets gentle. The slope is gentle there, and it flattens out. Only this time it's a negative slope. So if you were to find the amount of magnesium that remains after 1 minute, then you would find 1 minute on your axis, draw a dotted line which intercepts your graph, draw a tangent at that point, and you measure your change in y, and you divide by your change in x. So in this case, it's 0.72 divided by your time, which is 1 minute 40 seconds, the change in x. So that particular point, if we divide those two, our rate is 0.0072 grams per second. So this can be done even with reactants, the amount of reactant that remains, or you can even use the amount of reactant that is used up. You will still get the same. So this is important for you to be able to do. And here I'm just going to introduce the factors that would affect the speed of a reaction. We have temperature, we have surface area, we have concentration or pressure for gaseous reactions, and we have a catalyst. So we're going to do a full video on this, but you must understand what is called the collision theory, which says that for particles to react, they have to collide with each other with sufficient energy, which is called activation energy. So you need energy to kickstart the reaction, which you call activation energy, and it has to be sufficient to enable the reaction to start. When there's less energy than the activation energy, then nothing will happen. So here are the main factors that would affect your speed of reaction, which is the amount of energy in the particles, and also the frequency of the collisions. So if you have more frequent collisions, then you're going to have more successful collisions. Successful collisions are collisions which would result in the formation of a product. So the more frequent your collisions are, the more likely you're going to have successful collisions, and hence you're going to have a higher rate of reaction when you have a higher frequency of collision. So we're going to look at this in detail, but the two main points here are the amount of energy the particles have and also the frequency of collisions. So when you look at these factors, you should remember that you should try to think of how temperature is going to affect either the amount of energy the particles have or the frequency of collisions. So this is how you explain each of these factors, from temperature, surface area, catalyst, concentration, or pressure. So I'll meet you in another video where we'll discuss this in full detail.